All right, open up your book to section 5-3. We're on page 254 in your book. And the title of this section is Sine and Cosine Functions. And our objective here in this section is to extend the definitions of sine and cosine to any angle. If I were to ask you right now what you know about sine and cosine, you'd probably say SOHCAHTOA. You recognize the relationships for a right triangle, having sides called the opposite side, the adjacent side, and the hypotenuse, that there's a known relationship between those ratios of those sides to give you the sine, cosine, or even tangent of a given angle in that triangle. And we're trying to extend this to any angle, so I want to be able to go beyond just right triangles, is what we want to eventually get to here. All right, so let's start out with a definition here of a periodic function. A periodic function is a function whose values will repeat at a regular interval. So if you looked at a sketch, for example, like a sine wave that we might have sketched here, a sine wave we would say is periodic because it keeps repeating itself. It goes from a high point to a low point and back up to that same high point, and then just repeats that over and over and over again. A couple of terms that we use to describe this periodic function. When it repeats itself at regular intervals, we got ourselves a periodic function. The two terms that we use to describe the parts of this sketch here, we call, first of all, the graph itself, I've marked that in red, the cycle. So the cycle is referring to the actual function values and the actual sketch of that function that you'd see. Versus the period of that function is the distance it is horizontally from one point to the same corresponding point later on down the line. The period we'll see will be defined as that shortest distance there, but those are two terms we use to describe a periodic function, and they are different. I want to make sure that's important, or that's stressed here, that you understand the importance between the difference here, that the period is actually a horizontal distance we're measuring, versus the cycle is the graph itself. The actual y values that the function's going through is the cycle. All right, so here's our definition then of a periodic function, or this is one way to define what a periodic function is. F of x is a periodic function if and only if there exists some number p, which has to be positive, the period is always positive, such that f of x minus p is equal to f of x for all x in the domain. Now, it's a lot to that, but let's break this down a little bit here. First of all, they're saying there's some number p, so p is just some number out there, and it's positive. And this little equation that they give us here, f of x minus p, well, we've seen stuff like that before. In fact, if we go back to chapter 1 and we think about transformations of functions, this is just a horizontal translation of your function. F of x minus p would mean take your function and shift it p units, and you end up with the same thing that you started with. It's equal to f of x. So if you can take your function, shift it p units to the right, and you end up with the exact same function you started with, then that means that you've got yourself a periodic function. And one last thing here about that value p, the smallest such number p, and it's a positive number that we're talking about, the smallest positive number p that you can come up with is called the period of the function. You know, if the period turns out to be 1, then it turns out you could shift your graph by 1 unit or 2 units or 3 units or 4 units, and those would all give you the same graph that you started with. But the smallest such one is what we call the period. So the period in that case would be the 1. All right, so let's talk about sine and cosine, or SOHCAHTOA. Actually, we're not going to worry about the TOA part here today. That'll be a discussion for a later time. We'll just deal with sine and cosine. And again, that SOHCAHTOA there, the S is for sine, the C is for cosine, the O is for the opposite, and the H is for hypotenuse. The A and the Ka part of that is the adjacent side, and again, the H is for hypotenuse. So it's just a nice little way to remember the relationships for each of these trig functions. So if you're dealing with angles in a right triangle, which is probably, again, the extent of your knowledge at this point of sine and cosine, then we can draw a right triangle that looks something like this. We'll mark our angle theta. I'll even mark the direction of it, although since it's in a triangle, we don't usually worry about marking the direction. But I have the adjacent side. I'm abbreviating that ADJ there for adjacent. This is one of the sides of my angle. In this case, it would actually be the initial side of my angle. The hypotenuse is the terminal side of my angle, and the opposite side is the side of that triangle that is not one of the two rays that makes up the angle. So there is our right triangle with the three sides labeled and our angle theta. And it turns out then, again, this is what SOHCAHTOA tells us here, is that the sine of theta is equal to the ratio of the opposite side over the hypotenuse. The opposite side divided by the hypotenuse gives you the sine of your angle. And the cosine of your angle, theta, is equal to the adjacent side over the hypotenuse. Again, that's the ka part of SOHCAHTOA. All right, so that's what we know from right triangle trigonometry. Hopefully that's something that we're carrying in with us here as we walk into precalculus, that we know those basic ideas about right triangles. But as the objective of this section indicated, we're trying to extend this beyond just working with right triangles or angles that are in a right triangle. I want to extend this to any angle. So how do we do that? Well, we can take an angle and we can mark it in standard position. Remember that for an angle to be in standard position, that means that you've got the vertex at the origin, so that's what we've got here. And I'm going to measure this angle here counterclockwise, so that means I'm measuring in a positive direction. And the initial side there is along the positive horizontal axis, the positive x-axis. So there's our angle in standard position. And on my terminal side, I just have it going through some point UV. There's obviously lots of points that fall on that terminal side, but I've picked one of them and I've named it UV. So if I want to figure out what the sine of this angle would be, or what the cosine of this angle would be, what I could do is I could actually draw in what we call the reference triangle here to help me do that. If I'm in the first quadrant, I can do this. But this will extend to any quadrant if I define it based on these points UV. But if I draw this reference triangle in here, which I've got sketched, and I label the sides of that triangle based on that point. That point there, that x value of that point is telling you how far from the y-axis that point is, which is exactly what the base of this triangle is. The horizontal leg of that triangle is u. The vertical leg of that triangle turns out to be equal to v. That's what v measures on a given point, uv in the coordinate system. V tells you how far you are from the x-axis. So that's what v is. And now if I use those names instead of adjacent and opposite and hypotenuse, but rather now I use u and v, and instead of calling the hypotenuse here, we're going to measure that distance and call it r. I can now use those replacements for adjacent, opposite, and hypotenuse. So the sine of theta, instead of being equal to the opposite over the hypotenuse, now becomes v over r. And the cosine of theta, instead of being adjacent over the hypotenuse, now becomes u over r. And as you can see there, r is just the hypotenuse of this right triangle. We can actually use our Pythagorean theorem to come up with what that distance is. R is going to be the square root of u squared plus v squared, and r is always going to be positive. When we're working with our definitions of our trig functions for angles measured in standard position, r is a positive value. U and v, on the other hand, could vary depending on what quadrant this point is marked in. In the first quadrant, we'll see that u and v are both positive, but in other quadrants, one might be negative and one might be positive, or they might both be negative. What this allows you to do now is it allows you to extend beyond working with just right triangles when we're dealing with sine and cosine. All right, so let's talk about the sign, S-I-G-N, of your sine and cosine functions. So if you're working in the first quadrant, as we just pointed out there, if we pick a point UV in the first quadrant, then it turns out that U is positive and V is positive. That's what I'm stating here, is that U is greater than 0 and V is greater than 0 if we're in the first quadrant. Or if you want to think of it as kind of an ordered pair, you could write it as a plus plus. There's another way that you could write that, where the plus plus, that notation I'm using, is to indicate that the x coordinate is positive and the y coordinate is positive. Now when you jump over to the second quadrant, in the second quadrant, you'll notice that now V is positive. That's the y value. That's positive. But now U has changed signs. U is now negative. We know that in the second quadrant, your x values are negative over there. So we could indicate that by saying that, again, we've got kind of an ordered pair here where the first coordinate is negative, but the second coordinate is positive. I could write that as a negative comma plus as a kind of an ordered pair to help me simplify that notation. And if I continue around to the third quadrant, down in the bottom left side of our Cartesian coordinates, now I've got that both my U and V are negative. They're both less than 0. So I can, again, indicate that as kind of an ordered pair here to indicate that both the x and the y coordinate are negative by putting that negative in parentheses there and separating those with a comma. And finally, if I wrap around here to the fourth quadrant, quadrant 4, we have that just V is negative, but now our horizontal is positive. The U value is positive, and that's what we know about the fourth quadrant. Your x values are positive there, but your y values are negative. Or again, you could write this as an ordered pair here and just say that the first number is positive, but the second number is negative. If we kind of put that in an ordered pair notation. This is important for us to know that what values U and V are equal to in terms of whether they're positive or negative. When I think about the definitions that we just wrote down up above for sine and cosine, we know that sine is based on the value of V. And since V changes from being positive in the first quadrant and in the second quadrant to being negative in the third and fourth quadrant, that means that if I'm talking about angles in the first or second quadrant, the sine value must be positive up there. But in the third or fourth quadrant, it must be negative. And I can do a similar analysis for cosine. In fact, we use a little acronym here to help us out here. It turns out that because both U and V are positive here, when you calculate the sine of any angle or the cosine of any angle in the first quadrant, that they are all positive in that first quadrant. All of your trig functions are positive there. Over here in the second quadrant, because U is negative over there, U being negative, U is the value that we use to calculate cosine, that means that only sine is the positive one in this quadrant. So I'm going to just write down sine. Sine's the only one positive there. It'll turn out that down here in the third quadrant, that tangent is the only one that's positive. Move that up here so I can write that down. So tangent will be the only one that's positive here in the third quadrant. And finally, when I wrap around to the fourth quadrant, again, because U is positive there, but V is negative, it turns out that cosine is the only one that's positive there. And the little acronym that we use to help us remember this, if you look at the first letter here that we've got written down, the A, the S, the T, and the C, the acronym that we usually use to remember that. Obviously, you can remember exactly those things, but sometimes you remember this by saying all, the A from the first quadrant, students, the S from the sine in the second quadrant, all students, take the T in the tangent from the third quadrant, and then calculus from the C in the fourth quadrant. If that helps you remember those, then you can use that little acronym. All students take calculus tells you which trig function is positive in which quadrant there. You'll also notice one other thing I can point out here for you is you may have wondered why we name the quadrants the way that we do. Well, notice that if we were to measure an angle in standard position, means that you're measuring in a positive direction in a counterclockwise way, that's the order you would actually go through those quadrants. Start in quadrant 1, and then as you move in a counterclockwise direction, you hit quadrant 2, then quadrant 3, and then quadrant 4. This is the reason that we name these the way we've named them, 1 through 4. One thing to note here, I guess, R is positive in all these quadrants. We mentioned that up above there when we were looking at the definitions for sine and cosine. But R is positive in all these, so that's why it doesn't matter what R actually is equal to. It's positive, so the ratio there in terms of being positive or negative is always going to be based on U and V. All right. So that brings us to what we call the unit circle. The unit circle, the name there is describing a circle, of course, and the reason why we use the word unit is because of the fact that it has a radius of 1. So the unit circle is actually a circle that's centered at our origin with a radius of 1. Anytime we talk about the unit circle, that's what we're referring to, a circle that's centered at the origin with a radius of 1. So in other words, it might look something like this here. That horizontal line that you see there, that's my x-axis, and the vertical line that you see there, that's my y-axis. We can name them if that makes that a little bit easier there. This is x, and this is y. And then I've got a circle with a radius of 1. So that means it crosses my x-axis there at 1. And then it crosses the y-axis at 1. As I continue around that unit circle there, I'll cross the x-axis again at -1, and then the y-axis again at -1, and back around to where I started. So that's my unit circle. Got a radius of 1, so it's got 2 x-intercepts, 2 y-intercepts. Let's take a look here at what I'd end up with if I go back to my definition of sine of theta and cosine of theta in terms of u, v, and r. And what would I end up with if I mark some points at some key values here? In particular, we're going to look at what's happening at each of my my axes. I hit my x-axis or my y-axis. Now, in the first column, I've just got values of theta listed. In the second column, I'm going to calculate the sine of theta. You'll notice that I said that that's equal to v, is equal to just v. I didn't say it's equal to v over r. Now, the reason I've left r out is because r is the radius here. It's the distance you are from the origin, and you'll notice that for this here, we're talking about r is equal to 1. This is my value of r. So it's not that I'm leaving it out. I'm dividing by 1, which means that I can get rid of it there. And so sine of theta is just equal to v. Cosine of theta would be equal to just u. All right, so what do we end up with here? Let's mark a few points on our circle here, and then write down what sine of theta is equal to and cosine of theta is equal to at each of these points. So this point right here on my unit circle would be the point x is 1, y is 0. Or that is u equals 1 and v equals 0. So the sine of theta is the v value, so sine of theta would be equal to 0. And the cosine of theta is just u over r, but again, that's 1 over 1, that's just 1. All right, if I continue around my circle here, let's get to this point right here. That's at x is 0, y is 1, or that's the ordered pair. If I think of it as uv, again, that's u equals 0, v equals 1. So since sine of theta, or sine of 90 degrees, is equal to v, that would be v is 1. And cosine of theta is equal to u, so that's 0. And continuing around here, when we get around to this point right here, this is 180 degrees. Again, we're looking at this measurement right here. I'll mark this one here since I got some space to mark this one. I'm talking about this angle right here, theta equals 180 degrees now. So this point right here is on the terminal side of that angle. And that would be the point at -1, 0. So since sine of theta is equal to v over r, and r here is 1, it's equal to just v, which is 0. And cosine is the u value, that's a -1. And let's continue around here to this point right here. That's 0, -1. So sine of theta is equal to a -1 then, that's the v. And cosine of theta, cosine of 270 would be equal to 0. That's the u value. And actually, as I come back around to 360, I'm back to the same point I started at. So that's the same ordered pair there, 1, 0. So that means the sine of theta is v, so that's 0. And the cosine of theta is u, which is 1. And at this point, it would start to repeat. You can now see why this must be a periodic function, because now that I get back around to 360, I'm just doing the exact same thing I just did with the same points and getting the same results. It's periodic. It's going to repeat every 360 degrees is what I just figured out. Let's see if we can actually sketch what these functions look like. Can we actually draw a sketch of what the sine of theta and what the cosine of theta would look like? Let's start out with the sine of theta, since that was my first column up above. And I want to look at the theta values as being my x-axis, and the sine values that I came up with as my y-axis. So it looks like my theta values need to go from 0 to 360, and my sine values, I get a value of -1 as my lowest and +1 is my highest. So that gives me an idea of how I can set up my axes here. Let's mark these. So I'm going to make this +1, and I'll approximate that to be -1 down there. And I'm going to call this 360 then. We'll just sketch one period of this. And so halfway in between that would be 180, and halfway in between those would be 90 and 270. All right, so we've got a couple of marks here along each of our axes here. All right, so now let's plot some points that we came up with, and then we'll sketch the curve that goes through those points. So starting out at theta is equal to 0 degrees, it turns out sine is equal to 0 at that point, because sine is equal to the vertical component, the v value, and that's 0 there right on the x-axis. At 90 degrees, sine is equal to 1, so I got to plot a point up here. At 180, sine is back to 0. At 270, sine goes down to -1. Sine is at -1, somewhere about right there. And then finally at 360, we're back to 0. So now let's see if we can sketch a nice smooth curve that goes through those points and see what we end up with. So I'd end up with something that kind of does that right there. That is our sine function. This is y is equal to the sine of theta. And you can see that once I hit 360, I'm going to repeat this. This has a period of 360 degrees is what that tells me. All right, let's do the same thing for cosine here. Let's mark these points here roughly about the same spots. So there's 1, here's -1, and we're going to call 360 way out here. I'll divide that in half to call that 180, and half again is 90, and then halfway between 180 and 270, or sorry, is 360 is 270. All right, so now let's plot the points that we came up with for cosine. So that's the third column that I've got there. So again, at 0 degrees, cosine was at 1. So at 0 degrees, we're up here at 1. At 90 degrees, it gave us a value of 0, so we drop down to 0. At 180 degrees, cosine is a -1. Again, that's the third column of numbers I'm looking at up above. And then at 270, we're back up to 0. And then finally, at 360, we hit our high point again as 1, it looks like. And again, let's try to sketch a nice smooth curve here, although you could probably sketch this with a kind of a V shape, but it's going to have a nice smooth curve that goes through here. So it's going to do something kind of like this. That right there is our cosine function. Y equals cosine of theta. Again, you can see that it's going to repeat itself. Once I hit 360, I'm back to where I started with at theta equals 0 degrees. So this is going to be periodic again. It's going to repeat itself every 360 degrees. So that is the period of this function. All right, let's take a look at a couple of examples here. Look at example 1 there on page 257. It says to draw an angle theta equal to 147 degrees in standard position, and then draw the reference angle. Well, I guess let's first mark down what angle they've given us here. They told us that angle theta is equal to 147. So again, if you need to mark some axes and what their values are, then do so. That's 0. Here's 90. Here's 180. So I know in between is 90 and 180. So 147 is just over halfway through this second quadrant. So this would be our angle theta. Draw the reference angle. So the reference angle, let me draw that in a different color here. Call this theta sub r. And that's the angle between the terminal side and the horizontal axis, and it's a positive acute angle, so that's the angle that we've got sketched. And it says to show the measure of the reference angle. All right, so let's measure that then. We did this in the last section. We should be able to do it again here. Theta sub r is equal to, you just take the difference of these two angles here, the 180 right here and the 147 right there, the difference of those two. 180 minus 147, that looks like that is 33 degrees. So our reference angle is 33 degrees. And then it says to find the cosine of 147 degrees and the cosine of the reference angle. All right, so let's see if we can do that then. Let's do this in black here. So I've got to find the cosine of theta, which is 147 degrees. And I've got to find the cosine of my reference angle, which is 33 degrees. All right. Well, I can tell you that before I even start this, we know something about the sine, S-I-G-N, of these numbers. If we're talking about an angle that's in the first quadrant, 33 degrees is an angle that's between 0 and 90. That would be an angle in the first quadrant if I were to sketch that angle in standard position. And I know all of my trig functions are positive there. I'm expecting this is going to give me a positive answer. Versus 147 degrees, that right there is in the second quadrant. And your x values are negative there. That is, your u value is negative. This is going to end up being a negative number. So I know I'm not going to get the same answer here when I go to calculate this, but I am curious to find out what the relationship is between the original angle and the reference angle. So let's grab our calculator and try that out. All right, so with your calculator, one thing you need to make sure that you do is you need to make sure you are in degree mode. So if you're not in degree mode, then come and switch it out of being radian mode and switch it back over to degree mode. So let's take the cosine of 147 degrees, which we already said we know is going to be a negative number, negative 0.8386 it looks like. I'm going to go ahead and calculate the reference angle as well, which is the cosine of 33 degrees, and we already said that's going to be positive. We know we get a oh, check that out. One value is positive, one value is negative like we expected, but we actually get the same number otherwise. That seems interesting that we are getting the same result with the reference angle when we do that calculation. That probably leads us to think that there's a relationship here between our reference angle and our original angle, which we will see that is in fact the case. That's a cool little property there for us. So the cosine of 147 was a negative 0.839 if we round that. And a positive 0.839 for the cosine of 33 degrees. So yeah, it looks like if we're looking for a relationship between an angle and its reference angle, we're dealing with the cosine. Turns out that they just turned out to end up with the opposite sign, or I guess it depends on what quadrant we're working in as to whether or not it will be the opposite sign from the reference angle. All right, take a look at example 2. Example 2 says the terminal side of the angle theta contains the point 8, negative 5. So let's write down that point that they gave us, 8, negative 5. So sketch the angle in standard position and use the definitions of sine and cosine to find the sine of theta and the cosine of theta. All right, so let's sketch this. 8, negative 5, we'll call this 8, we'll call this negative 5. So that means we got some point down right here that's on the terminal side of our angle. I'll sketch my terminal side going through that point right there. All right. So this is the point 8, negative 5. Now they didn't tell me much about angle theta. They just tell me that it contains that terminal side. So I really don't know for sure if this is the angle theta. It could be a negative angle and it could go clockwise instead. It could wrap around a couple of times. I really don't know. It won't matter for this problem, but I'm going to go ahead and mark that as my angle theta here. I like marking that in standard position in a positive direction if I get to pick. I'm going to write it that way. If I want to find out what the cosine and the sine of theta are equal to, remember those are based on knowing u, v, and r. And I know u and v, but I don't know r. But the nice thing is I can calculate what r is equal to. R is equal to the square root of, it's just u squared, which is equal to 8 squared, plus r squared, which is a negative 5 squared. So what does that turn out to be? 64 and 25. What's that give us? 64 and 25 is 89, right? Square root of 89 is our value for r. And now with that, I should be able to calculate what the sine and cosine of theta are equal to. I know that the sine of theta is equal to v over r. And v is equal to a negative 5, and r we just calculated was that square root. So I can write this as negative 5 over the square root of 89. And again, if you think about what sine, S-I-G-N, you should end up with here, if I think of my acronym there, all students take calculus. If we're in the fourth quadrant, the only angle that should, or the only trig function that should be positive is cosine. I'd expect sine to be negative. We did end up with a negative. That's a good thing. Let's calculate the cosine of theta. We'll do the cosine of theta. That's equal to u over r. So u is the value of 8 there. So that's 8 divided by r, we said was the square root of 89. So 8 over the square root of 89. And you'll just leave your answers just like that. You don't need to rationalize the denominator to get that radical out of the denominator. You don't need to punch that into your calculator to get an approximation for this. Leave this in this form. That's our desired result. Is actually written just like this. All right. That's all I wanted to do for example 2. Let's do one last example here on page 258. Example number 3 says to let y equal 4 times the sine of theta. And it says, what transformations of the parent function is this? And then a copy of the graph there of this image of the sinusoid. Okay, sketch your sketch by plotting the parent sinusoid and the transformed sinusoid. All right, so we'll plot both of these here together. But first thing they want us to do is indicate what's happening here. So you got to go back to what we learned back in chapter 1. We already know what sine is going to look like. We sketched that just a couple of slides back. If I talk about multiplying that by 4, I know that right there is a vertical translation. Or vertical dilation, sorry. It's a transformation, but it's a vertical dilation. We're going to stretch this function by a factor of 4. So I should see that it goes 4 times as high as it's gone in the past, or the original, and 4 times as low as the original would go. So let's sketch these together. So we'll say that this is at 0. We'll say that this is at 360. And we've got 1, 2, 3, 4. 1, 2, 3, 4. If I mark my vertical axes there. In fact, let me mark a couple of points here along my x. We'll call that 180. We'll call this 270. And this right here will be 90. All right. So the sine function, you might have to go back and refresh your memory on what sine looked like. But sine was the function that started out at the origin. And then at 90 degrees, it was at its high point. At 180, it's back to the origin. At 270, it's at its low point of -1, and then it's back to the origin there at 360. All right, now this one looks like it hugs the x-axis a little bit more, and that's because I've tried to go from 4 to -4 in my sketch here. So it should be a -4 down here. All right, now what does it look like when I stretch this by a factor of 4? That means that at 90, instead of being at 1, I'm going to expect to be up here at a value of +4. At 270, instead of being at -1, I'm going to expect to be down here at -4. And of course, multiplying the zeros by anything is going to still end up giving me 0. So now my sketch does this. It goes up to +4, comes down to 0, down to -4, and back up to 0. That right there is our sketch of what y equals 4 sine of theta looks like. All right, and that right there is the end of section 5-3.